Greetings, geologists, and welcome to our first lecture, one of many in historical geology. Some lectures are going to be short, some are going to be longer, most have multiple pieces. So this one's fairly short, but it has some very important foundations of which you need to pull from for the rest of the semester. So I'd like to start off the semester by saying, what do you see in the picture? Besides a gorgeous set of rocks, what do you see? Most of you have taken physical. It's a state requirement now for state transfer credits. And so physical geology would have taught you about how these magnificent rocks in Zion National Park were formed. But there's a story there. There's a geologic history dated in this rocks. I will tell you there was a time not too far in the distant past where people thought that these rocks were just laid down by a flood, that that's why they were there. So I'm going to challenge you, regardless of what your religious beliefs are, to think about the rock record, to think about the fossil record, and I'll define each here shortly. I grew up in a very, very strong church-going family. Both were scientists, my parents were, but they wanted us to understand geologic time versus what human time conception is, and understand that they were two very, very different things. The humans made the clock, and why should we put those parameters in what we were learning about in terms of God at church? So I can't even begin to go down the road of where you sit on your religious beliefs. You may have none, and that's fine too. But I want to hit this one head on because this is the first thing that people struggle with in historical geology, is this geologic time issue. So we're not here to debate, did it occur or not? There's enough evidence to show that there is a thing called geologic time. I think what we'll wrestle with is what's in our hearts. Again, I'm not trying to challenge what you believe in. I'm asking you to learn more factual information so you can come to a good, solid foundation of decisions about what you believe in. So let's get started. Understanding geologic time is super important, and a couple of terms come to mind that we'll be using all semester: the rock record and the fossil record. What does that really mean? One day a student asked me that, and I'm like, well, it's what's out there in nature. And they're like, you mean like a round black record that you play on a record thing? That's an antique in my house. And I'm like, no, not that kind of record. And I understood for the first time, I guess, that people perceive that in a different way than I do, simply because of my experience. It's just an automatic reflex to say rock record. So I think it merits some definitions here. These are some rock record from Zion National Park in Utah. Those crossbeds are rock records. They give us a glimpse into the geologic past, and they're evidence that this event occurred that created them. That's all a rock record is. It is evidence that's still with us in the form of rock layers. So fossil record would be the same for fossils. In other words, we have fossils in rock layers, like this rock strata right here, and the fossils that are there help tell a story. So whatever we have in the recorded rock record or fossil record is what we go with our scientific data. Let me be blunt. That's why science changes. Regardless of what field you're in, and especially geology, the more data you collect, the better the science will be, because it can be tested. Your hypothesis can be retested, and then you can determine if you were accurate about your initial hypothesis or not. So the bottom line is, geology without fieldwork is not a science that's going to grow. That's how we got to where we are today, and why the people we're fixing to learn about are so critical to the overall story of what you'll be learning over this course. So let's get started in understanding that we'll be applying some general principles that you'll learn about a little later to rocks in order to solve problems, in order to differentiate between different layers and different depositional environments, and how those rock layers were deposited. All of that being part of the rock record and the clues in which we interpret to help make good decisions about geologic time. There are two types of ways that we measure time. We'll be revisiting in much more detail these same concepts. Relative dating just simply puts a series of events in order based on relative information, like fossils. While I can age date fossils to a degree, I really need other rock layers to date those fossils because most fossils have carbon base in them, and so that carbon's probably long gone if it's more than 70,000 years old. So absolute dating is where we use isotopic or radiometric dating to help put an accurate time frame to a rock layer. Now we use a dual approach. The dual approach is important because the dual approach tells us more about the timescale and what happens within it. But let me be clear, discoveries that we find in the field will change this. So if this is our partner at Mesa Lands Community College, and he's a PhD in paleontology, his name's Axel, he's talking about phytosaur jaws, and phytosaurs have a very specific range. So if we were to find and discover phytosaurs outside of their range, that would change the geologic timescale and change the data that we have to work with. So that is why it is imperative in the field of study of geology that one spends time outdoors and in the lab to collect and analyze samples and fossils and rocks in order to interpret the timescale properly. So where does the Earth's history begin? It begins by answering this question. Where does human history start? Genesis states that the Earth is approximately 6,000 years old. So is that true or is it not? Well, I know it's at least 6,000 years old, but I suspect that it's much older than that based on fossil and rock record. But until the 18th century, even the late 18th century at that, people believed that things like this ammonite right here were simply on land because of a big giant flood that happened that was described in Genesis. I am not refuting that this flood happened, but nevertheless, there are other flooding events that are much more substantial in terms of a rock record that we have for it. So we need to investigate a little bit more. Let's start with the gentleman that actually put a clock date to the creationism of the Earth. And he stated that on Sunday, October 23rd, 4004 BC, based on the genealogy of people denoted in the book of Genesis, James Ussher produced this date, and it was accepted by the church as doctrine. So people believed it. And not to believe it was actually an act of heresy. So let's get a little bit further into this and talk about some of the important people. Genesis evidence, again, suggested that all of the debris that got piled up on continents, that made up hills, that made up rock formations, was caused by this flood, as we know of Noah's flood. Also, in the Genesis account and evidence of the Earth's history, erosion of the Earth suggested that the end times of the Earth were near. So if you look at back when the Genesis was being developed, and you think about the early writings of the Old Testament and how far they date back, that means the end of the Earth's been around since almost the beginning of man. And I would suspect that'll be true until the end of the Earth occurs. And I am not one to judge how or when that will occur. So everywhere erosion was witnessed, like you see right here in Olympic National Park, that would have suggested that the Earth was being beaten down, that it was eroding and going away, which was evidence in Genesis of the coming of the end days. Cosmogenists came up with another theory that was important to trying to answer questions about the Earth's history. Am I saying any of these are right or wrong? I'm saying that there's room for data collection in all of them. Their theory said the Earth was hot, glowed like a sun, and as it cooled, it created a primitive crust that formed. Later on, water and atmosphere became separated due to relative densities, and the interior of the Earth had a fiery core surrounded by a solid material. Now, we know that is not true anymore based on PNS waves, which are primary and secondary waves. So that particular part of the theory is incorrect. But you have to imagine these were thoughts that were over 200 years old. So people were trying to come up with better educated guesses without much data to support it. The key is to get out there and find the information to help draw the right conclusions. Georges Louis de Buffon published a very important book that redated the Earth at 75,000 years. And he based this on the studies that he did of Halley's Comet and concluded that the Earth had cooled during 6 specific epochs, and that total time frame of 75,000 years was a maximum age of the Earth. And his famous quote from this book, "A year is to God as 1,000 years is to man." Well, there may be some truth to that. Not saying literally. I'm saying that I think time is something that humans have conceptualized. So if you are a believer in an almighty being, I think you have to consider that maybe we put some restrictions on that almighty being if we put a clock to it. Anyhow, this gentleman's work was a major turning point thinking for the estimated age of the Earth. Another theory that was important to the development of geologic history was Neptunism. It has since been disproven, but it's important to take a look at it. A.G. Warner in 1787 basically had 3 key points about what he considered a world ocean. Number 1 is this universal ocean existed, and this is how most of the known rocks on Earth were created. He wasn't too far off base in understanding that we have a lot of marine rocks on continents, and how did they get there? Number 2, that all mountains were assumed to be the leftovers from the original creation. And number 3, succession of rock layers reflected gradual shrinking of the sea and emergence of the land. There is truth to that with regressions. Although he didn't quite get the transgression thing, I think he understood that there had been an ocean that covered land, even though it was before we even recognized transgressions and regressions. So this guy played a pioneer role in starting to see things with a different point of view. He came up with 4 distinctive categories of rocks, and I might add this is important because it actually applies to part of the geologic timescale. He referred to primitive rocks as those that contain no fossils and are made up of a chemical origin. They are found in high cores of mountain ranges, so you'd be looking at igneous and metamorphic rock in particular, and that the earliest rock precipitated from the sea. Well, we know that granites and gneisses and schists do not come from the sea, so he was off base there, but he did know that there were some very old rocks, what I might correlate for later in the course as Precambrian. Number 2 type rock was a transition rock. These were deposited rock layers that contain fossils as the initial sea level dropped, and these rocks contained the first mechanically formed rock layers from gray rocky sandstones and some limestones. Well, we know that limestone's not mechanically formed, it's chemically formed, so he was off base there, but he at least understood that there was a methodology for creating detrital sedimentary rocks. Number 3, he termed the coin secondary rocks. These are included lower topographic deposits and flat layered rocks such as sandstones, limestones, gypsums, rock salts, coals, basalts, things that were laid down, meaning on land. Number 4 were alluvial rocks. That alluvial is still a term used today. These were the areas that fill the lowland and basins with non-marine rocks like from rivers and lakes. So that term is actually still used as a description for modern day river deposits called alluvium. That particular term has been kept. Another guy is going to turn the corner that is considered the father of modern geology and the father of the rock cycle, and it's one of the many gentlemen that understood deep time and brought it to light and was not necessarily came without some resistance for his thoughts. So let's look at him. This is James Hutton. James Hutton was a Scottish farmer. He had some different thoughts on how the rocks got here that were on the planet. And first of all, he said rocks exposed to the atmosphere tend to weather into gravels into soils based on what he saw on his Scottish farm. Number 2, he said that the earth had a balance between destruction and rejuvenation of itself. In other words, rocks were constantly being made and being destroyed. Number 3, Earth is internally dynamic and it's constantly changing, so this process of rejuvenation and destruction will continue. And number 4, because the rocks seem to reveal the results of ordinary processes such as those we can observe now. In other words, the present is the key to the past, which is Uniformitarianism. It's the principle of that. It should have taken substantial more time than 6,000 years to create the rock layers that we have on the planet. So he was one of the first that really challenged that 6,000 year marker for the age of the Earth. Not too popular of a decision, I might add, at that time. Some challenges made by James Hutton on Neptunism. He said steeply tilted transition and secondary rocks in mountains originally had been deposited flat, not in their tilted manner. You got to go back to the law of original horizontality and realize that these rocks had been laid down flat. He said valleys were cut by rivers rather than huge oceanic floods. And this is an example of that called Artist Point in Yellowstone. He said, if we assume that the Earth is 6,000 years old at its maximum capacity age, we must subscribe to catastrophic changes to explain geologic facts. In other words, everything has to be created by a catastrophic event like a flood. He goes, I know that's not true because I can see layers of soil being made on my farm even in my lifetime. He compared the state of the 2,000-year-old Roman wall in northern England to the length of time that is needed for an ordinary geologic process to occur, meaning it would be very slow. He was like, well, if the 2,000-year-old Roman wall here is in pretty good shape, the Earth must be older than 6,000 years because it takes a long time to make rock material, period. So he had some pretty compelling thoughts on his new concept of geologic time. He also said primitive strata could not be chemical in origin because the presence of pebbles and sand grains within these of the rocks that he studied in Scotland, specifically schist, proved the existence of older rocks somewhere from geologic past. In other words, these older rocks got eroded and pieces of them got put into this particular type of schist rock. So primitive strata were not lacking in fossils, he said, too. He goes, just because it's old, I've seen fossils in some of these older rock layers. He recognized that no rock layer in the strict sense could be considered primitive. So the closest thing we have to describing what primitive is really, really old Archean Precambrian rocks. Even then, there is chemical suggestion that there could be fossils there. So he really kind of just said the primitive thing's out. You can't call that. But the closest thing we have to that is Precambrian in age. So Plutonism was the theory that replaced this thought process, and he basically said this. James Hutton said, the present is the key to the past, and normal, ordinary processes happen on a day in and day out basis. However, we will have catastrophic events such as flooding, earthquakes, tsunamis, so forth. So one of his points was that mineral veins and things like granites and schists found in northern Scotland formed through crystallization of hot fluid materials known as magma. So here's some igneous dikes right here that have gone through this particular chunk of granite from the Grand Teton Range. He also stated that seawater did not contain all the necessary compounds that could create such mineral veins, that you would have to have other sources of the minerals in order to create them. He hypothesized, but didn't prove at the time, that there was great pressure and heat sources inside the Earth. He understood the premise that there had to have been a heat source. He just wasn't sure what it was at that time. If he'd lived a couple of hundred more years, he would have lived to see radiometric dating and isotopic dating, and he would have loved the chemistry labs that we have today. He proposed that the Earth's internal heat also consolidated sediments and then caused them to come up to the surface in an upheavaling process, as what we know as mountain building. He stated that dikes of granite then cut across older rock layers, intruding and making these dikes and sills of what we now call plutonic features. And he proved this by finding dikes and schist in central and western Scotland. So he found material like this and said, this looks like a cross-cutting relationship. And he pretty much came up with the foundation of cross-cutting relationship, that anything that crosses over something else by definition must be younger than what it crosses over. He also identified there was a big chunk of missing time in the rock record, and that's an understatement. He discovered a great unconformity in the rock record between the secondary and older rocks, and he said this is like a major gap in time This was proof of a great upheaval of mountains, which now we know to be true. Grand Canyon is a case in point where Rodinia was a supercontinent that created massively huge mountains. Those have eroded down, and these are the cores of what's left of those mountains right there. He found pebbles worn down from older rocks just above the unconformity, which suggested that they had been eroded. He observed steep dips of rock layers below the unconformity and correlated that with Steno's principle of original horizontality. So these are some famous things that James Hutton came up with. And mind you, he was a Scottish man that studied rocks in his area. And just from his small travels that he had, he was able to come up with some revolutionary thoughts on how to think about geologic time differently. He identified the source of mountains. He said that the discovery of the unconformity in the dikes proved that mountains were formed from repetitious dynamic uplift of the Earth's crust, which we now know is true. He didn't know how, necessarily. We would later prove that after World War II. He disproved the theories that mountains were caused by the flood and that they formed from the Earth's primeval surface. In other words, he disproved the theories. He disproved the theories that the flood created all the rock material we have on Earth and that the original mountains and so forth were from flooding and from the initial creation of the Earth. He actually showed a mechanism by which mountains could be uplifted. Then there came a guy by the name of Charles Lyell. He wrote a book called Principles of Geology, which was initially published in 1830 and has been revised, I am not joking, 12 different times, with the last edition of which I've read cover to cover in 1975. Maybe a new one will come out before long. Nevertheless, he had a totally extreme view of uniformitarianism in comparison to James Hutton. They did not see eye to eye. James Hutton did not say that there could be no catastrophic events, but essentially Lyell had a completely different view. He stated that violent events such as earthquakes occur, but no more frequently in one epoch than another. So basically things are the same. Geologically, we should expect the same number of earthquakes, the same number of tsunamis, the same number of meteorite strikes, so forth. He envisioned that conditions remained essentially constant throughout all of geologic time, and he was credited with the most extreme view of uniformitarianism. However, his thoughts on principles of geology would change the field of study forever. Sir William Thomson, known as Lord Kelvin, which is also the guy that the Kelvin scale is measured after, came up with a completely radical new set of thoughts that challenged Lyell's principles of geology. In essence, he basically said, hey, the solar system that we got had to come from some kind of impressive beginning that was a much more literally heated up situation from when it first started to what it is now. In other words, it's gradually cooling off and the Earth is doing the same thing. He stated that equilibrium can occur on a temporary basis, but there will be upset throughout geologic time in a balance of an ecosystem and certainly throughout the solar system. He concluded history was not strictly uniform, but that it has indeed changed and will continue to change and sometimes abruptly change throughout geologic past. This grand impact that Lord Kelvin had literally changed the thinking patterns of people because he came up with what we know to be true today, which is the Earth is in a constant state of change, which is the theme of our course. The history of the Earth shows that. The rock record shows that. The fossil record shows that. The extinctions we'll talk about indicate this. The evolution of organisms define this, and it's evident everywhere we look, from microscopic to macroscopic to megafauna. He said history never repeats itself exactly the same way, and he said irreversible changes in and on Earth have resulted in the evolution of two distinctive things. One, Earth itself, meaning all of the earthen materials such as minerals, rocks, elements. Number two, life, meaning anything that's living. So I would have to agree with that because these trees right here, this is from the petrified forest, these species of trees are extinct. They never happened again. So Lord Kelvin was on to something. He would need some more refinement of his work, which that's still going on today, but he really changed the field of science dramatically and, challenged what the founding guy of geology, our first two really big guys in geology, had to say. The more accurate view of modern uniformitarianism is called actualism. The term actualism actually means actual or present day causes. It allows geologists to study Earth's processes in real time. In other words, for example, Mount St. Helens over here to the right, this is the pyroclastic flow and lahar deposit that's actually on site at Mount St. Helens in Washington State. And he said, if we know how this occurred, actually witnessed it in 1980, we can apply present day processes to geologic past as a clue. So some clues may lead a geologist to predict that a specific set of circumstances could have occurred or have occurred in geologic past, even though we cannot see them yet in the rock record. Doesn't mean they're not there. It is a hypothesis which leads us to go look. A case in point, black smokers. We knew that deep sea vents existed before we ever found them. So sometimes a scientist knows that things are there. We just have to go look and find them in the field. Again, my purpose for saying that this course, you can't just read, you can't just do some lab work and expect to get it. You have to go out there and find the data and then analyze it and then correlate it with your writings and your readings. So it's very important you take all those steps in order to have accurate data. So let's apply what you know. The stromatolites on the left are from Shark Bay, Australia. The stromatolites on the right are Precambrian in age. They are from Glacier National Park. So understanding the present is the key to the past, and we'll look at it from an actualism point of view here. These, since I know how they form today in tidal flats and salty marine shallow areas, I can hypothesize that that's how this rock formed as well. So that's where we're going to start our next lecture series, and it's going to become more complex as we go through this, but I want to challenge you just to think about what you've learned for a little bit, contemplate the time thing before you jump into learning about the geologic time scale, and let this kind of rest with you for a little bit. All I'm asking is that you consider, keep an open mind, that we've got a rock record and a fossil record that indicates substantial time needed to deposit these rock formations. So I'll see you at the next lecture. Bye.